Hey, this is Steven from RC Engineering, and welcome to my first video on I guess my community development. I haven't really came up with a name yet, but it's kind of my workbench video series where I work on different projects that I then release, obviously in video form and open source form to the community. So this is the very first video. This is my second video. The first video was just kind of announcing the series, and so these will be released weekly. They will include any sort of development I do, any sort of scratch building that I do will be included in this as well. So pretty much anything that doesn't necessarily involve flying. It involves working at the bench the workbench, quote unquote, to get to that flying point, or to learn some more things about engineering, using RC models for stuff, obviously boats, cars, planes, quadcopters, helis, basically aerospace, anything that runs on the ground and anything that runs in the water, right? So we're going to be doing a few different videos over the course of this series. At the end of each month, the very last weekend of the month, you'll have a video from the Rule of Thumb series, talking about looking at some engineering principles, using equations and stuff like that. So I have a few of those coming up. Also, I'm going to mention again right now and at the end, go ahead and if you want to support these videos and you like what I do as far as this development and other things on my channel, go ahead and check in the description for my Patreon page and become a Patreon to support my videos on my channel to help me do more interesting things in videos. I will probably come up eventually with some some backing tiers that directly correlate to this guy. Maybe like send out some prototypes to you guys or something if they could be mass produced or something like that. Or if I'm going to go into production, or if I'm going to go into small production with it, have you guys be kind of the early, the beta, almost like flight test beta builders, where you guys test it and help me with making adjustments. Okay. So, in this video, I'm really getting into the brushed motors, and the main one that I've been getting into is a Tiny Whoop, and eventually I want to build a 1020, a 1025, a 1025 coreless brushed motor build. If you guys don't know, the regular brushed motors of the Tiny Whoop are 615s. So I wanted to build a larger one that could be flown outside that's just slightly heavier. So with that being said, and also messing with the brushed Tiny Whoops, I really want to be able to track the differences that are made with the props. So recently on one of my videos eventually coming up, I did a test of taking the 4-blade props from the Tiny Whoop and cutting them down to 2-blade props. And when doing so, what type of losses am I having? So I found a large flight time increase from 2 minutes and 30 seconds, and increasing an additional 40 seconds when I cut the props down to 4 minutes and 12 seconds or something like that. It's like another 30 to 40 second increase. And so would like to know why that is. Is it just from the weight of cutting the props off? Is it because of the increased efficiency, because there's less load and the motors are running at higher RPM, thus more energy efficient, as you'll see in my Rule of Thumb DC Motors series? Is the prop more efficient at that speed? So we have the motor more efficient and the prop more efficient? Or is it just a combination of the weight and the efficiency? So what I wanted to build to test that is I have a few high precision scales around the house. I have one that goes up to a hundredth of a gram scale, so those are the standard like $15 scales. And then I have one of those jewelry scales that will do like 100 or 50 grams, but very, very, I think it goes to a thousandth of a gram. So very, very accurate scale. So the first thing I was going to do was build a basic stand for brushed that will be able to use that particular design, and then be able to pivot to hit the scale in order to show what thrust is in grams. Then I would like to eventually expand it where we have the where we could look at the amperage and the voltage rating of a battery and be able to graph it to determine the best props for brushed and brushless eventually. Eventually I'm going to make a brushless one. So the best props for brushed and brushless to get maximum efficiency, maximum power, maximum weight, maximize weight, or minimize weight. What I mean by maximize performance, minimize weight, or maximize efficiency and minimize weight, something like that. So to have a nice graph and different props, so that either you guys could go to my channel and I'll have videos about it and you guys could check into that, or you could maybe go to, I'll probably publish it on Thingiverse or my website if I have it by then. You guys could go there to download that and do your own testing, where you build it and buy a scale or whatever, and buy whatever electronics that are needed, Arduino and an amp reader or amp tracker or amp sensor, voltage sensor, and be able to plot it, and also RPM sensor to be able to plot it and make your own determinations. Or maybe at that time I go into small production of it and I have a few kits, so you guys could, if you guys don't have a 3D printer, because I'm going to be utilizing my Trinus, or I call it the Trinus, it's probably Trinus, but I call it the Trinus 3D printer to 3D print a lot of parts. So if you guys don't have the 3D printer, I'll try to make it available to where either you ask a friend to 3D print it or you buy a kit from me, and so you can do your own testing. So first thing I did, and what I'm going to do always in these videos, is I take a look at some of the things that are already out there and see how we could make adjustments on that. So there's a few pretty cool ones where they make use of already existing scales, and they kind of modify them. So this one, I'm guessing, pivots. And we'll go over the engineering principles of these guys and how they work and how they measure. Also in this video. So this one uses a few different load cells. So I'll show you guys those. These right here are load cells. So what the load cells do, and pretty much all of these are going to use load cells, and every scale uses a load cell. What a load cell does is it has something called a strain gauge, which is some wires that go through this part here. And then what happens is, I believe they're resistive in measurement. So when the metal flexes, you'll have an increase in resistance, and you'll have like a Wheatstone bridge, which is a arrangement of 4 resistors in a square type with, I think it's 1 or 2 going through the middle, going across. So it's kind of like a square with 2 cross hatches through it with resistors. I can't exactly remember. I sort of know how they work. I just use them, but I sort of know how they work, so I'm going to explain it. So when they flex, the resistance increases, and because you're pushing voltage through it, you could read the current change or the voltage change. You feed a specific amount of current through a constant amount of current, and then read the voltage change, the voltage drop through the sensor. So that's one way. I mean, well, that is the way that it's done. And you could determine that force by 3D modeling this design, and then looking at what force it takes to push this bridge down. So you say, okay, 50 grams or whatever, pushing here, pushing at the edge will cause this piece to flex 1 millimeter, let's say, even though that's very exaggerated. That's a very high flex. Let's say it's a tenth of a millimeter, 0.1 millimeter. And 0.1 millimeter will go to this resistive number, right? So let's say 5 ohms or whatever. And you say, okay, well, 50 grams or whatever I said at the beginning. I already forgot what I said. 50 grams to flex 0.1 millimeter is equals to 5 ohms. So 5 ohms is equal to 50 grams. Pretty much that's how that works. So basically what he did is he took all of these guys out, all these little cheap load cells, and you can see they got, this is basically on the bottom side, this is the feet side. So by pushing something on top, you can see that it will push all this force in here to try to bend this this little tab piece here. And you see that it's pretty weak there from the first picture. From this picture, you can see that it's pretty weak here because they want to see drastic changes. That way they can do fine measurements. Because if it was really thick here and it would barely bend, you would need to apply a lot of force. That's why also a lot of load cells will have a rating on them. They'll say 500 grams or 1 kilogram or whatever. So that's why you'll see some of the scales will say up to 500 grams or whatever, because past that point, the resistors cannot measure anymore, pretty much. And also, if you go too far, you will permanently deform these load cells. So yeah, so this is kind of the idea of integrating an already existing scale into one, but I want to show you guys the conventional kind of one. So here's from the same guy. So here's kind of a conventional one. So you have so basically you have what's called a lever arm, and we're going to be talking about torque, which is a measurement of turning force, and units are force times distance. So generally what you do with these kind of rocker styles, which is the style that we're going to design one, and we're going to design one that fits 6, 7, 8.5, and 10 millimeter brushed motors for small micro brush quads. So you'll basically install your motor here, and then this guy looks like it's going to be pushing down. The force is pushing down, so this is going to go up. Because one of Newton's laws is any force that stays basically still, static, requires an equal and opposite reaction force, right? So if this goes up, right, 10 newtons, and it's not moving, so let's say this guy presses, so obviously if this guy goes up, this piece is going to go down because it's connected right here on a lever. So when this guy goes up, this guy goes down. Once it goes down, it's going to go down and it's going to hit the scale. And when it hits this scale, this piece is no longer going to move upwards. So that's known as now the system is static. It is not moving, right? So that's why when we talk about, some people have static models. The models don't move. They're not electrically powered or anything like that. They're just for display. So when this guy goes up high enough and this goes down to hit the scale, now the system is in static equilibrium. So this force upwards translates to this down force over here, and they have to be equal and opposite to prevent the system from moving. So there are some very important things to have in this system. Number one, what's very important to not have any inconsistencies on the scale side. If we were doing a microcontroller, we could adjust for this. But if you're doing a scale, a very unintelligent scale where it just measures force, right? You can't program the scale like an Arduino. But one of the most important parts is to have the exact same distance from one side to another. So otherwise the torque will be different, right? So this distance from this pivot point to the motor has to be the same distance the other way as well, from this pivot point to the scale. as you see, this guy's 3D printed, and this guy's huge moment arm on here. So I mean, that's not going to be what we're going to use, because right here on the Trinus or Trinus, I only have a 5x5 print area. So this guy has got to be very tight and very compact. But in our so that's basically one of our restrictions to design around, is this 5" by 5" platen here on the 3D printer. So that's one thing that we have to look into, is that this distance and this distance is the exact same. So let's talk about why that is that way. So, you know, I might as well inject some engineering principles in these videos as well. So, 1 second. Okay, so basically this force right here going up, let's look at the torques. So force is in either meters, Newton meter, sorry, not Newton meter, newtons, or kilogram force, I guess you could say, or pound force, or slugs. We're going to use pound force, right? Or we could use newtons, right? So let's say that this is, let me write this down so I stay consistent. So let's say this is 5 newtons. And these will be I'll be going over all this stuff in some of the rule of thumb series, so I won't worry about it. So this force going upwards, let's say, is 5 newtons, right? So this prop is pulling at 5 newtons, but in this case we're going to measure grams. Usually they don't measure in newtons, they measure in grams. So let's say it's 50 grams, right? 50 grams force, not mass. Force and mass are different. I'll go into that later. 50 grams in a later rule of thumb series. 50 grams of force going upwards, right? And then we want to measure torque. So torque is force times distance. And the torque, all you have to do to find the distance to determine the torque is the distance of the moment arm. And we're just going to assume that this is straight. Let's just say that this motor was attached right here. Because if it goes up like this, you have to also have another secondary. You have to take the cross product, which we're not going to go into. We're just going to treat that this is attached to the top here. So now we have 50 grams of force. Now we have to have this moment arm here. Let's say that that is in meters. Let's just say that for whatever reason that's 0.5 meters. So that's 250 and then 1 point. So that's 25 gram meters, which sounds really weird. Because usually they're either foot pounds, inch pounds, or Newton meters, Newton time meters, right? So you could do this with this example. You could do with any measurement, any sort of unit, as long as you keep them consistent between the two. Okay, so this is 25 gram meters, right? Now, in order for this guy to stay static, it needs to also have the same counteracting force down here, same reactive force, because we're going to use fusion to design, and in fusion they call it reactive force, which is also, like I said, the equal and opposite force. So that's a 25 gram meters on one side, so that has to be equal to whatever force we have on this side. But let's modify something. So like I said, ideally this is supposed to be the same distance, but let's say that that is actually 0.35 meters. Okay, so now we have 25 gram meters equals to 0.35 meters, and then we have one unknown. So what is the force going to read on that scale? So 0.25, I can show it up here. 25 equals 0.35 times x, and then x is the force that's going to be measured on the display of the scale. So I pull out my calculator. 25 divided by 0.35 is equal to 71 grams. So you see right there, 50. So we started out with, on this side, this is picking up at 50 grams of force, but our scale is reading 71 grams, so that is incorrect. So that's why we need to have the same exact length, because otherwise this will give a scale above what it's actually doing. However, we can use this to our advantage. So let's say we have a 500 gram load cell, but we have a brushless motor. Let's say we're doing it for brushed right now, but let's say we had a brushless motor, and that brushless motor is doing like 2 kilograms of force, which is 2,000 grams, right? And then our scale could only handle 500 grams. So what we could actually do is make this guy longer. You can make this guy longer, and then that will show less force over here, and then we could just multiply it by, we could just do this simple calculation on it to figure out what the actual force is. So we could use this to mechanically scale the force down that it puts down on the scale. So let's say you have a massive motor, but yet you only have a scale that could read up to 1/100 of a gram that can only do 500 grams. Because usually when scales are very accurate, they're rated for a very low force. So for example, that jewelry one that I have for, you know, diamonds and stuff, that goes to a thousandth of a gram. Yeah, thousandth of a gram, but that could only weigh 50 grams, right? That's okay for most of these brush motors, but once you get into brushless, let's say you're doing 1 kilogram, how can I scale that 1 kilogram down so I can measure it accurately up to a thousandth of a gram? You make this moment arm a lot longer. So showing that, instead of having a 0.35 meter, we have a 50 gram equals to, let's say it's a point, let's say this is 0.6 meters, right? So now if we apply a 50 gram force on, oh sorry, I said a 25 gram. So 25 gram torque, which is 50 gram force on this side, divided by 0.6. So here, if we added, if we doubled this length, if this length was double this length, and we put 50 grams of force upwards here, and this was double that length, we would only see 41 grams here. So that way we've scaled down our force. But obviously if you do massive motor on this side, this thing has to be hella long. So that's the idea. And in this particular video, I think we're just going to kind of go over like what these thrust stands are, and then we're going to look at some, talk about some, and then next video we'll get to designing it so we could do some testing on some. So here's kind of the scale that I have. In here you see that the pivot guy is down here. And this one's also 3D printed. Pretty much everything on Thingiverse is 3D printed or laser cut. I do not have a laser, I have a 3D printer, so that's what I'm going to use. You see here, actually I just noticed this is a picture of a woman here. I didn't see that. Anyways, so here we have the moment arm straight up, and then this is straight across, and then this ideally is the same length from here to here as it is from here to here. And so here he has a whole bunch of he's got a 2200 battery in there, and then I don't know if he's got a servo tester. I think that's a servo. I think that's the servo tester. But having the servo tester on there is probably a bad idea because you're touching it and now it's causing weird ripples and stuff. But he also puts an ESC in there. So then eventually we're going to change it to a brushed and brushless capable thrust stand. So here's one of Turnigy's original thrust stands. And here they're putting a tachometer here, a laser, looks like, a photo gate. Oh, it's a Turnigy tack. So here is their version. So here's the, so this is trying to go this way, right? And then this guy is going to pull on this load cell here. This is a beam style load cell. So you'll see it here from the original stand. So here's a beam style load cell. And what it has is it has very deep cuts here inside to make this side and this side of the beam very thin. That way, when you apply very little forces, you'll have flex in this aluminum beam. It's made out of aluminum. And then on this side and on the back side, they have strain gauges which measure the bend of the material and a force, a resistance. And by doing testing to find out what resistance equals what deflection, they could figure out the force. And by figuring out the force, they have this guy accurately or very precisely machined. And so using something like fusion and applying a force here, they'll be able to figure out the displacement that this guy moves. So let's say if I push down on this steel about 50 grams, let's use 50 grams again, and let's say it deflects 0.1 millimeters. Right, 50 grams, 0.1 millimeters. So that, let's say we look at that, and we look at what it says in the resistance, and it says it's 25 ohms. So 25 ohms is equal to 50 grams. Right. So you would use that to equate, and you do that through a whole bunch of testing, and then you get an equation from that to take that measurement. So here's kind of the old school style. But what we're going to do is we're going to make use of a scale, a very accurate scale, to measure what we need to measure. And so I think on these videos I'm going to make them about 30 minutes long, so we have a few more minutes here. So let's go ahead and take a look at what we have and how we're going to get started in Fusion. So this is Fusion 360, which is a free set of software that you could download. You could apply for an academic version, or if you don't want to apply for an academic version, you could download it for free, and it's free until you make a certain amount of money per year as a startup. So that basically is free for startups. So that's basically where the line is for them between a startup and a full-size company. So I have here a new folder called RC Engineering. And here we're just going to do a few things where we're going to draw a few things here in Fusion. My default scale is in inches, and the first thing I'm going to do is I'm going to draw a rectangle, and I'm going to draw out the bounds of my 3D printer. So these are what is limiting my design. And so I'm going to keep those two things in mind, that the motor has to be the same distance from the pivot point as where the pressing piece is pressing down on my scale. But we want enough distance where we could get prop clearance, and also we need to know which way the prop is turning, right? So if the prop is going up, then the other side has to be pressing down on the scale. So for this guy, I'm thinking that the prop is going to push down because I want to have it compact. I can't really do, because this line to this line obviously is a hypotenuse. The hypotenuse is only 7 inches and 71 thousandths across. So I could do that and have this be my center point, but then I don't really have much room here. So I could do that, but it's going to take up more space. It's not going to be as storable. I'd rather have it be vertically, so it would kind of like have this kind of from here to here, from here to here, and then that would be what would be used. So I'm thinking maybe something like this. And then obviously here I probably want to have a 90-degree angle like that. So that now that's perpendicular. And then obviously, like I said, these two have to be the exact same length. And this also is determinant on the size of props that I'm going to use. So so if this was the case, I need to have the propeller go inside here so that it turns downwards. So that means that I need at least that much clearance, and then this guy right here will press down on the scale. or it could be the other way around. This guy presses down on the scale, blades are inside. So if this is my pivot point, I'm going to put a point for my pivot point. So if that's my pivot point, I can't have this guy pressing down on the scale. So that's a pivot point, and this is my press point. So I can't have this guy pressing down on the scale, and then this guy with the motor on here pulling this way. So I can't have the motor pulling this way because this guy's not pressing down on scale. It's going to pull this motor this way, and then this is going to pick up, right? 1 second, I need to sneeze. Sorry. So the motor has to be on the inside, but this is going to help keep it more compact by having the motor on the inside. And then also this is going to be very small, so we need millimeters to inches. So the biggest motors usually for brushed, if they're not geared, is maybe 66 millimeters, which is almost 2.6 inches. But I have some geared large canned motors that turn 6-inch blades, so that will probably have to have a different setup. But we want to keep this one compact for right now. If I want to have a different one, I'll change the model, and then so I don't have to store that big old one all the time. So let's make this 3 inches to handle that size, or yeah, let's do 3 inches. So it'll do even bigger. So you see now we're past this point here. So what I could do here is I can make this horizontal and change the distance from here to here to be 2 inches. Okay, so we're at 32 minutes. So that's kind of the end of this intro video on this particular topic. So I hope you guys like this video. If you like this video, please subscribe to make sure that you don't miss next week's video and all the rest of my content. And if you like my videos and you would like to support my channel, please check out the link. In the link is a direct link to my Patreon. In the description is a direct link to my Patreon, and then you could support my videos from there, or you can keep watching, and all the ads that you see will help me with my channel there as well. Alright, so it's been Steven from RC Engineering. I'd like to thank you guys for watching. If you like this video, please subscribe, and I'll see you guys, and check the description for Patreon link, and I'll see you guys next video. Thanks for watching. Take it easy. Peace.